All right, AP Physics, here's your most missed questions for the first rotation multiple choice review. There's not as many on this one, so good job to those who are taking it. This problem asks you to do a differential equation. So it says a windmill is spinning because of the non-uniform force of the wind. The windmill is originally spinning at a speed of omega 0 or omega naught, and the crosswind slows it with an angular acceleration of negative a times omega squared. So this is an acceleration that depends on your velocity. And that will look very similar to our terminal velocity problems. The question asks, what will the angular speed be when the speed of the windmill at time t? So I need to know a function, omega, as a function of t. Well, how do I do that? Well, I need to write my equation for the acceleration. Acceleration is equal to negative a omega squared, which is given to you in the problem. You can rewrite your acceleration here as a derivative. And if I write it as a time derivative, it's the rate of change of your omega with respect to time. I can separate my variables. So now I have a differential equation. I have the derivative of something, and this omega is not a constant. This is changing over time. So as the velocity of the windmill decreases, so does the acceleration of the windmill, and omega will get smaller and smaller over time, and so will the acceleration. So how do I solve this? You need to separate your variables. So I need all the omegas on the same side and the dt on the other side. So if I swap those around, I'd get this expression. Then I can integrate both sides of this. And if you integrate both sides of this, you'd get this. 1 over a times omega would equal t. And then the plus c, I'd have a plus c on both sides of this. I'm just going to put the plus c on the right side. You could combine those constants. We know from the problem that time t equals 0, we have omega 0. They define that for us. So I can plug in 0 for my time, and then I can plug in omega 0 for my velocity here, and I can solve for c. And if you solve for c, you get this. C is equal to 1 over a times omega naught. And if I plug that back in for c, now I just need to solve my equation for this omega. This is my function. This omega right here is the function I want, omega as a function of time. So I just need to do some algebraic manipulation here. I take everything on the right side and divide it and multiply by the omega to get it on the right side. And you get this. Your a would cancel, and then the a would distribute to the t. So it'd be a times all of this. And then I want to get rid of that omega, the fraction, the denominator. So I'm going to substitute that out or factor that out. And if you factor that out, you'd have to add omega here, and you can do the math to show that these are the same. Well, if you divide by fractions, it's the same as multiplying by the reciprocal, and you end up with this. And that's one of your answers. So this would be your function. If you gave me any time, and I'd calculate it by plugging in your t value right here, I could tell you the angular velocity at any moment in time. And this problem asks for the time capital T. And so that function is right here. That's your a. So this is a great review of how you integrate a differential equation to get a function of time. Okay, our next one, you have two uniform spheres, x and y, and they roll without slipping along a horizontal surface. Sphere y has 2 times the radius, so that's our 2r right here, and 4 times the mass, and 1/2 the translational speed of sphere x. So we've got a lot of variables going on here. The rotational inertia of a sphere is 1/2 mr squared. If ky is the kinetic energy of sphere y, kx is kinetic energy of sphere x, what's the ratio? Well, let's just write our equations here. How do you get the kinetic energy? They're rolling without slipping. What does that mean? That means that for x here, I'll write it down below so we can divide them. We'll have kx on the bottom and ky on top. So ky is going to be the 1/2 m, the mass of it, which would be 4m, 1/2 mv squared, and our v is 1/2 of v. So I'm going to do 1/2 v squared. Plus, I also have rotational kinetic energy, so that's 1/2 I omega squared. And your rotational inertia of your sphere is 1/2 mr squared. So I'm going to do 1/2 times, here's my I value, 1/2 m, which would be 4m, r squared, and then times omega squared. And omega squared, that relates to your 1/2 variable right here. Remember, velocity is equal to omega times r. So omega is your velocity divided by your radius. And so I can plug that in here. It'd be 1/2 v over my radius r. and then this is going to be squared. I'm going to do the same thing for my little sphere. My little sphere is 1/2 mv squared, and it's just m, plus 1/2, my I for my little sphere would be 1/2, just mr squared, times v over r, quantity squared. And now you just have to cancel everything that cancels, combine like terms, and figure out what that comes out to. And if you do that, the answer, it comes out to a 1 right here, to your E. In other words, the top and the bottom are the same. And I'll let you do the algebra for that. Okay, our next one. A motor drives a shaft of radius r divided by 8 that's attached to the center of a wheel of radius r. The motor is turned off. The force that the motor exerts on the shaft is F. So this would be still accelerating. It's a positive force. It varies with time as shown. There's also a constant friction force of 0.4 newtons applied to the rim of the wheel in the opposite direction of motion. During which time interval does the rotational kinetic energy increase and then decrease? Well, the rotational kinetic energy, that's 1/2 I omega squared. And how would this increase or decrease? Well, the I isn't going to change. And so the only thing that could change is this. So what the question's really asking is, when is the acceleration positive? If it's positive, then our omega term is increasing. That would be an increase in kinetic energy. And when does it turn negative? And that'd be our decrease in energy. So that's related to your torque. And so you want to look at your torque, and the torque due to the friction on this has to equal the torque of the motor at the point where your acceleration is 0. At every point where the friction is higher than the torque of the motor, then we're decelerating. And at every point where the torque due to friction is lower, then we're accelerating still. So my torque of friction would be 0.4, my force times my radius. The force friction acts on that inner radius of r. And then the force of the motor, the outer radius of r. The force of the motor acts on the inner radius of 1/8 r. So this would be my torque of my motor. If you solve this for your force of the motor, the radius is canceled and you get 3.2 newtons. So when the force of the motor is equal to 3.2 newtons, we have no acceleration. For all values past this, the force of the motor is small enough that the frictional torque is larger. So we're decelerating on this side and we're accelerating on this side. And so it's going to be right in that range, 3 to 5 seconds. At 5 seconds, it looks like you hit 3. We're right at the halfway point according to our slope here. And so it's just before your 5 seconds, we'd have it changed, and that's how you get C. This problem asks you about different circular objects that are given an initial velocity, and they go up this little ramp here. This would be going against gravity, and it comes off the top. And they shoot these at different velocities. They slow them down until they get the perfect velocity where it comes off and it doesn't quite reach the top. So we don't want it to make it through the full arc. And they give you different cylinders here. This is the conceptual understanding that you want to do to solve this problem. This object here, if it gets up to the top here and can't quite make it around, that means it doesn't have enough energy. This is an energy approach problem. And all the objects have the same mass and same radius, which is important because I can do an energy approach to this and say that all the objects need to go up this little loop here. And that means the change in potential energy would be equal to mgh. And if they are all the same mass, all of these objects have to have the same energy to get up this little ramp here. Now, where does that energy come from? It comes from your kinetic energy. And the kinetic energy for an object rolling is 1/2 mv squared plus 1/2 I omega squared. It has this rotational energy as well. Well, for all these objects, this term is going to look exactly the same. The mass is the same, and you're changing your velocity. But for the object's rotational inertia, it changes this term right here. And the best way to think about it is this. We want to know which of the following from fastest to slowest speed to make it through the arc. So we want to list from which one do we need to shoot the fastest, which one do we need to shoot the slowest. Well, if I increase that velocity, I need to have a large velocity. This term needs to be large for all of the objects that have a small rotational inertia. If an object has a really large rotational inertia, I can have a smaller velocity, and that lower velocity, in addition to my rotational inertia, will give me enough energy to get up this little arc here. So if I have an object with no rotational inertia, you can picture it that way. If you have an object with no rotational inertia, and this term was 0, all of that energy would have to come from the translational velocity. And we would have to have a high velocity for that object to go up. So the higher the rotational inertia, the less velocity you need. So let's look up our rotational inertias. Here they are. Here's my highest rotational inertia. And then these are in order. Oh, they're not in order. So the Hall cylinder would have the highest, and then the Hall sphere would have the next highest. But the one that needs the largest velocity is one with the lowest rotational inertia. So that's your solid sphere. So we're going to look at our list here. Solid spheres are first. What's our next? The next lowest would be right here. Solid cylinder, then solid sphere. Let's see. Do I have those? 1/2, 2/5. Oh, yes. Solid sphere would be the lowest, sorry. And the solid cylinder would be the next. So solid sphere, then solid cylinder, and then your hollow sphere, and then your hollow cylinder would have the most with mr squared. So this one just has the largest I, and therefore it needs the least velocity to make it up that ramp. Our next one, a solid sphere is placed on a frictionless floor in a very long corridor. It's given a quick push so that it begins to slide without rotating along the corridor. It's in a frictionless floor. And then it says, how would the angular speed of the sphere be changing if the floor were not frictionless? If it were not frictionless, that initial push would give it too high of a velocity here for it to be rotating without slipping. So it'd continue to slip for a little while. And what that would look like is you'd have a frictional force opposing the motion this way, and it would be a kinetic friction force at first. And then it would turn to a static friction force when it's rolling without slipping. But what's happening is this force would apply a torque, and that torque would cause an angular acceleration. And that angular acceleration for this particular object is what would get the object rolling. And that rolling motion eventually would end up being rolling without slipping. And when it's rolling without slipping, this would turn into a static friction force. Now, during the transition between the kinetic friction and static friction force, that's what it's asking about. What would happen to the angular speed of the sphere? Well, it's going to start out, because it's accelerating, it's going to start out at 0, and then it's going to accelerate up to this, v equals omega times r, at which it would be rolling without slipping, and that's going to happen rather quickly. So it would be increasing, angular speed would be increasing until the slipping between the sphere and the force stops, and at that point, this would be satisfied. Velocity would equal omega times r, and that's your answer for that particular problem. Our next one, a projectile mass 0.2 kilograms is fired at this weird shape here, our sun shape, and its initial velocity is given to us. It collides with the end of the blade. The rotational inertia of the turbine is given to us. Assume the loss of energy. This is probably where those who missed this problem didn't interpret this correctly. Assume the loss of energy of the projectile in the collision is completely transferred to the blade. So you would, if you first read this, you would be thinking momentum. But we're not using momentum because the problem tells us about the energy. So this object is going to lose energy, and it's going to transfer energy into our little sun shape here. And it causes them to spin, the final rebound velocity of the projectile. So we have a final velocity and initial velocity. So my change in energy for this little mass would be my kinetic final minus my kinetic initial. And that change in energy is what gets transferred to this little sun shape here, and it causes the sun shape to rotate. Well, when it rotates, your rotational kinetic energy is equal to 1/2 I omega squared for this particular object. They gave us the I value. We're going to solve for the change in kinetic energy, so we have this, and we can solve for omega from that. So here's your math for that. I'll scroll down to the bottom here. This would be your initial kinetic energy. That's your total energy in your system, equals your total final energy, which would be the final energy of the ball, and the final energy of the rotating sun mass. If you plug in your values there, your negative here, we're squaring our final velocity of that object. It doesn't matter that it rebounded. This is not momentum. Energy is not a vector. It's just a scalar. And this gets squared, so it comes out to positive value, and you get 5.5 radians per second. So your correct answer is B right here. If you start to think about this with the momentum approach, you're having the right thought process. We just don't use it in this particular problem because they didn't give us a radius here. You'd have to have a radius to calculate your initial momentum. Yeah. That's it for your rotation problems. I hope that helps.